So now in part C, we would like to calculate the point probabilities for the mixed Poisson process, and in particular show that the number of claims up until time t in the mixed Poisson process is not Poisson distributed. So in that sense, there is something it does not share with the Poisson process that we know, the traditional Poisson process that we know. So the first thing we can do is to actually show that n of t is not Poisson distributed. And we kind of cheat a little bit because we look in the book, and if you take the book, chapter 2-3 on mixed Poisson processes, and you look at page 68, equation 2,349, it tells you that the variance of n of t is greater than the mean of n of t. And this is also what we call over-dispersion. However, in a Poisson distribution, the variance is equal to the mean in a Poisson distribution. In fact, both are equal to the parameter of the Poisson distribution in question. So it cannot hold. So thus, or so, n of t cannot be Poisson distributed. Now, one might ask, well, if n of t is not Poisson distributed, then how is it distributed? And that is what we will try to take a quick look at. And it will not be very hard, fortunately. So we will want to calculate the probability that n of t is equal to n. And we just recall that the definition of n of t is that we take a standard homogeneous Poisson process and evaluate it in the time theta t, where theta is a random variable. And because theta is a random variable, we want to try to get a grip on what it is by conditioning on it and then taking the expectation outside. So just the standard trick that we always use when we don't know what to do. Then we look at this and then we realize that given theta, n tilde of theta t is Poisson distributed with parameter theta t, right? So this is something that we may conclude because theta and n tilde are independent. So given theta, then whatever is inside here just has a value because of the independence, and then it just has the value of theta, and then the n tilde of theta t will be Poisson distributed with parameter theta t. And let's just write this and then have point probability given as e to the minus theta t multiplied by, what is it? I think it's theta t to the minus n factorial. So we can just plug that in there, and what we get is the mean value of e to the minus theta t theta t to the minus n factorial. And this is, in fact, well, we can just try to take out some of the stuff that we already know does not. I think this is just an n. Sorry, I don't know why I wrote the minus here. So t to the n divided by n factorial, and then inside I have the mean value of e to the minus theta multiplied by theta to the n. And I will have to calculate this thing if I want to know more about the distribution of n of t. And the value of this expectation depends on the distribution of theta. So I can't really go further without knowing the distribution of theta. In the next exercise, we will look at what happens when we assume that theta is gamma distributed. And we will conclude that in that case, the n of t will become negative binomially distributed. So that will be a very interesting case, and we'll look at that in the next video.